Hello everyone. How a wave interacts with matter. What is the consequences of this interaction? What's happened at electronic level during the wave matter interaction? What is the role of Beer-Lambert's law in this interaction? I, Dr. Nitesh Jaiswal, going to discuss all these things in this video, which is the part 2 of electronic spectra of transition metal complexes. In part 1, we have discussed why things appear colorful, what is the principle of complementary color, and the energy of wave, visible lights, and others. It is a very fundamental science that when a wave passes through a matter, it interacts with the matter and there is a change occur in electronic levels. First time in 1760, Lambert discussed the interaction of wave in solution. Lambert stated that the intensity of transmitted light is proportional to the intensity of incident light and the path length. And in that continuation, Beers in 1852 state the transmission of a incident light is proportional to the concentration and path length of the solution. In other words, the transmittance remain constant if the product of concentration and path length remain constant. Here you can see that transmittance proportional to the concentration and path length, and intensity of transmitted light proportional to the intensity of incident light and path length. I is intensity of transmitted light, I naught is intensity of incident light. Later on, these both law has been combined, and that is stated as Beer-Lambert's law, which give the absorbance and concentration path length relation. According to Beer-Lambert's law, the absorbance of a solution is proportional to the path length and concentration of the solution. That is, A is equal to epsilon LC, and that A is absorbance, and that absorbance is equal to log I up naught upon I. I naught is intensity of incident light, original light, that is I naught, which is striking on the solution, and I is the transmitted light, which is transmitted after passing from the solution, and L is the path length of that solution. So how much light has been absorbed by the solution? That is equal to E is equal to epsilon LC. Epsilon is molar absorptivity. It is also known as molar extension coefficient. It is specific for every substance and matter. C is the concentration, L is the path length. Path length is generally described in centimeter, and A is absorbance. Absorbance is unitless and dimensionless quantity. Beer-Lambert's law has some limitation. This law is valid until the solution is homogeneous, the incident light is monochromatic, and there is no scattering when it passes through the solution, and the passing of incident light should be parallel. It passes through the solution parallelly, and solution should be homogeneous, and there should be no scattering when it passes through the solution, and the light should be monochromatic. These are few points. When these points fulfill, then Beer-Lambert's law follow. A is equal to ELC. This Beer-Lambert's law is very important in spectrophotometer. In spectrophotometer, we obtain a spectra, and that spectra is the relation of absorbance versus wavelength. And sometimes this absorbance is replaced with molar absorptivity or molar extent coefficient. As you can see here, there is a relation, there is a graph, there is a spectra between epsilon and wave number. Wavelength can be converted to wave number. the absorbance is inversely related to transmittance. If the absorbance is high, transmittance will be low. It means if there is 100% transmission, then it means there is 0% absorption. Yeah. In other words, if there is 100% absorbance, then the transmittance will be 0. The relation between absorbance and transmittance is absorbance A equal to log 1 upon transmittance. In an electronic spectra, absorbance, transmittance and molar absorptivity can be used to draw a spectra with respect to wavelength. Now the question, how this absorption of waves occur at electronic level? Since every atom is made up of electron, and electron reside in a energy orbital, and the electronic configuration which is lower in energy will be more stable and more feasible. The energy of electron or electronic level basically depend upon two things. One is the repulsion between two electrons in same orbital, that is Coulombic repulsion, and the exchange energy of same spin electron from one orbital to another orbital. Let's understand by example. Here I have taken the example of carbon, where the last electronic configuration is 2p2. There is 2 electrons which can be arranged in 3 ways. First is first is like this way, where the both electron reside in same orbital in anti-parallel manner. Second is this way, where the both electron remains in separate orbital in anti-parallel manner. And third is this way, where the both electron remains in separate orbital but in parallel manner, parallel spin. In these three, the third one is more stable configuration. The question, why? In first case, there is a Coulombic repulsion between two electrons because it is present in a same orbital. But in second case, there is two electrons present in different orbital, so there is less repulsion. It is more stable than first one. But in case of third, there is two electrons of same spin in two different orbitals, so their spin can be changed, means their orbital can be changed. Suppose this is first electron, this is second electron, so first second, and second can be go in first and first can be go in second. So there is probability of two type of arrangement. When there is maximum possibility of arrangement for stable configuration, then there is a more stabilization through exchange energy. There is one pair of exchange energy, so due to this exchange energy, this configuration will be more stable. So the ground state configuration of P2 will be like this. This follow the Hund's principle and Hund's principle. Now the electron in electronic labels have two type of motion. First is orbital motion and second is spin motion. The orbital motion generates orbital angular momentum and the spin motion generates spin angular momentum, and these both momentum couple with each other, means interact with each other, and this type of interaction is called coupling, that is Russell-Sunderson coupling or LS coupling. This is Russell-Sunderson coupling or LS coupling. In other words, you can understand this by this way also, that the spin momentum generate a magnetic field, orbital momentum generate also a magnetic field, and these both magnetic field can interact, and this interaction is called coupling, and that interaction produces a state, another electronic label, and that label is called what? Microstate, and that is represented by a new quantum number. That microstate is presented by a new quantum number, and that quantum number is capital L, total orbital angular momentum, and capital S. Capital L is the summation of small l, angular momentum quantum number, and capital S is summation of a small l, spin angular quantum number. There are n number of possibility of this type of coupling of two electrons or more electrons present in an atom, and that different possibility of coupling gives different electronic state or microstate. So there will be n number of microstate for a electronic configuration, and that microstate can be calculated by a formula. There is another coupling which is spin orbit coupling. When a individual electrons angular orbital angular momentum L and spin angular momentum S couple with each other, then that's called spin orbit coupling, and that's give small j. There is a difference between LS coupling and spin orbit coupling. LS coupling is a capital L capital S coupling, and spin orbital coupling is small l small s coupling, which give small j, while LS coupling give capital J, that is total angular momentum quantum number j. So when L and S couple, then they give j, but when small l and small s couples, then that is called spin orbit coupling, that is small j. So there is a difference, never mix with each other. This coupling results in microstate and different electronic labels with different energy. For example, here for a P2 configuration, I have taken, this is P2 configuration where the possibility of electron in this manner, 1 ampere. For this, the L value is +1 and 0 for second electron, and +1 by 2 and +1 by 2. So when we combine this, summation of small l, that will be +1, and summation of small s, that will be +1. So these are the notation which is called microstate. This combination of notation is called microstate. Such notation, there will be several number of such notation for a given configuration. What will that number? What is that different number? That can be calculated by this way. Total number of microstate in a system will be n factorial upon m factorial n minus m factorial. N is what? N is the maximum number of possible electron in a subcell. Suppose it's p orbital, there will be maximum 6 electron. Similarly, m is the number of electron presented in orbital. So let's see. Suppose for P2 configuration, there will be maximum 6 electron in p orbital, so this is 6 factorial upon, there will be present 2 electrons, so m value is 2, 6 minus 2, this is 6 factorial upon 2 factorial into 4 factorial, that is solving, and that's give 15. So for a P2 configuration, there will be maximum number of microstate will be 15. It means there is a possibility of 15 type of interaction coupling which give these interaction. You can see here this different type of possibility. The more stable possibility is first one. Okay, इस तरह से you can see this is the 15 microstate for P2. Similarly, you can calculate for D2 other configuration D1, D5, P2, P3, P4. For D2 it will be 45. So this lesson is end here. Next will be discussed in next video.